Hi all, and welcome to Physical Attraction. This episode is based on a combination of things. Partially it's based on a lecture I saw by the sociologist of science, Professor Harry Collins, and partially it's based on an article I wrote about that lecture for Singularity Hub. The general theme here is, why should we listen to scientists? There's a game young children like to play where they're just beginning to learn how to interact with the world, talk to others, and indulge in their natural curiosity. It's called the why game. Take some natural phenomenon. Why is it raining? Why do people die? Why is the sky blue? If you furnish the child with an answer, they'll inevitably ask why again, until you reach the limits of your knowledge, or more likely your patience, and snap back with an unsatisfying, because that's just how it is. Most people eventually grow out of the why game. This is partly because, as a conversational strategy, it's irritating. But also people come to terms, or at least attempt to come to terms, with there being a set of fundamental whys where answers won't necessarily be clear. You can fill this gap with your religion. The fundamental whys are the province of God or gods. Or you can do what I do and fill it with something really vague like the weak anthropic principle, and conclude to yourself that you're only ever going to observe a universe that appears well suited to host you, and that asking why, even in itself, presupposes a logic to the universe that probably doesn't exist. Any number of other philosophical explanations might satisfy you and break you out of this endless recursive loop of why. You can use a nice healthy dose of pragmatism and choose to worry about more pressing matters before trying to solve the mysteries of the universe. But the why game is still a useful one to play as an adult, testing each link in the chain of your beliefs, exploring your own motivations, and examining the trends and forces behind changes in society. If you do this, you can find out where you're making assumptions, and the assumptions that you're making probably are what most needs to be tested about your theory of how things work. So in this spirit, I'm going to ask a why question that's been more and more popular lately. Why should I listen to scientists? This question is leading politicians towards inaction on climate change, individuals towards not vaccinating their kids, and consumers to oppose genetically modified foods, just as social media, where every opinion seems to have equal weight, leads thousands of people into bizarre conspiracy theory wormholes. And it should be clear to everyone by now that the consequences of people questioning certain aspects of scientific advice, or the question of which group of people and which sources of information to trust, can have world-altering consequences. As the world grows more complex and interconnected, with threats from emerging technologies, biodiversity collapse and climate change, it's more than necessary than ever that we work together in a rational, constructive way. But when you start from irreconcilable standpoints about what is true, or even how to find truth, practical problem solving becomes impossible. So how can we persuade people that expertise isn't overrated? For many of the sciences, especially physics, the answer to this question was once obvious. The experts are right. Verifiably, nigh on indisputably, their theories have the power to make accurate predictions that competing worldviews simply can't make. Newtonian mechanics, when its laws are applied properly, could predict how the stars and planets would move far better than the vague theories of earlier eras. When Einstein's theory of general relativity superseded Newton's gravitational laws, this was confirmed by a famous expedition to observe the deflection of light during an eclipse in the Eddington expedition. This was a prediction that general relativity made, which Newton's gravity could not explain. In other words, our historical theory of hard physics has relied on verifiable evidence for truth. Indeed, this formed part of Karl Popper's definition of a good scientific theory. It has to be something that's specifically falsifiable. In other words, a good scientific theory could demonstrate its truth by telling you exactly what experiments you'd have to perform that confirms the theory to be true. On the surface, this line of argument is persuasive, but it's also flawed and far from universal. What if the theory is complicated enough that drawing that straight line, from theory to prediction to observation that confirms the theory, is far from obvious? An example of this might be if, for some reason, we can't make the observations that would confirm the theory. Climate change is a good example here. There are considerable debates at the moment about the climate sensitivity, essentially what temperature increase one would expect if one doubled the atmospheric CO2 concentration on Earth, as we are unfortunately on course to do at the moment. There are feedbacks in the system that might result in more or less temperature increase when we double atmospheric CO2. Now we can have expectations about how high this will be based on the law of conservation of energy, paleoclimate data, our best physical modelling as to what might happen, but we don't have great observations of the system because we've never done anything like this before, and we obviously don't want to find out by performing the experiment because the consequences could be disastrous and irreversible. Take theories or models surrounding epidemiology, for example, the effect of lockdowns during the coronavirus crisis. Again, it's not possible to just run the experiment and observe whether your theories are directly true, because lives are on the line. So in that case, why should people believe in your scientific theory if you can't provide evidence that it's obviously correct in this very specific circumstance. The invention of writing has allowed scientific and technological knowledge to accumulate over thousands of years, and people have had to specialise to a greater and greater degree. The age of polymaths who know everything is over, and, as the economists like to say, no individual person can make a pencil. Instead, more often than not, you have to study and hone your expertise for many years in ever narrower fields to make a contribution to our understanding of the world. In physics, for example, Nobel Prizes are not increasingly won by individual geniuses, but by ever larger collaborations of scientists running experiments that cost billions upon billions of dollars, and of course no one of them could tell you everything that's going on in the experiment as a whole. For this reason, it's just not feasible for us to expect people to attain a level of scientific competence in every single field. It's not going to be possible for you to be a world-leading biomedical scientist, climate scientist, physicist, chemist, drugs discovery specialist, medical doctor, epidemiologist, and ecologist all at once. In other words, much as I might wish I could learn all of these things, there are ultimately huge swathes of human knowledge that are inaccessible to me, and to you as well. There's just not enough time in a life. Therefore, we cannot all follow the same inexorable chain of logic, knowledge, observation, experiment, understanding, and so on that may have led individual experts in their field to hold particular beliefs, so that we are all as well informed as the scientists. And that means that certain things will have to be taken, to some degree or other, on trust. This is before we consider newer sciences with larger uncertainties attached. We've talked about climate science already as a prime example. The complexity and the inherent uncertainties associated with the system that's being analysed prevent us from making absolute statements about what will happen, about precisely how things will change. So, for example, precisely how rainfall patterns will shift if we continue to emit carbon dioxide into the atmosphere for the rest of the century. So scientists make predictions with uncertainties attached. When you read climate change reports like those from the IPCC, the claims are ranked according to confidence levels. Things like more greenhouse gas emissions will increase the temperature are practically certain with the current state of scientific knowledge, but precisely how complex systems like the Antarctic ice sheets will respond is still a subject for scientific inquiry and debate. Similarly, you're probably familiar with an endless parade of headlines proclaiming that red wine or chocolate or caffeine are good for you or bad for you. The human body is an extremely complex system, and a crisis of reproducibility means that many studies can be reattempted with contradictory results. So the question remains, why should we trust scientists? Well, in light of all of this, we must still persuade people of the truth, that science remains humanity's best tool by far to understand the universe, to survive, and to flourish in the future. That far from ignoring scientists and experts, we need them to take on a greater role in our society. And for that we need a different kind of faith. Trust that the institutions of science are behaving in an honest and rigorous way. We cannot simply answer the why question with "because science says so" and pretend that scientific knowledge is indisputable in all cases, even in areas where there's active debate. Equally, we can't give in to a sort of scientism, a desire to present science as some vast, all-knowing monolith, with PhDs as its high priests, who are infallible and whose word must be taken as correct. The reason we can't do this is because the argument from authority, "I know best, therefore listen to me," is inherently weak. If people don't recognise your authority, as is true with the anti-science movement, they might substitute it with a different authority, such as political figures, conspiracy theorists, or charlatans trying to defraud them. In the age of social media, where experts who've spent decades studying an issue have equal platforms with the gut instincts of strangers, and are often substantially less prominent than purveyors and peddlers of misinformation, people feel freer to believe whatever they prefer to be true. After all, it's just tweet versus tweet, and you will likely be able to find tens of thousands of people willing to like whatever incorrect sentiment you care to name, or even things that look like scientific papers or things that look like newspaper articles, which contradict the perspective that you don't want to hear about. Professor Harry Collins, a sociologist of science, suggests that rather than portraying science as a fount of utter certainty, we should instead focus on its values. If you present uncomfortable knowledge as reams of technical jargon, or handed down from on high by geniuses who you couldn't possibly understand, people will feel attacked in their beliefs and they won't want to follow what you're saying. You will end up preaching only to the choir, the people who already agree with you and trust you, because they're already willing to take the words of scientists on faith anyway. So the key to getting people to trust science isn't necessarily just about explaining the details of the science to them in excruciating detail, although of course scientific and mathematical literacy is always crucial to being a good citizen. Nor is it about talking down to people from a position of authority and telling them that only people with PhDs are allowed to proclaim on a particular topic. If you want people to trust science, you have to explain to them how it works as a system for forming beliefs and why it's superior to other such systems. Instead, Professor Collins would argue, we have to present the working method of the scientific community, and people will recognise values that they treasure. We should focus on how science works in practice rather than the details of the science. When it comes to forming your views on something, most people would agree that it's better to rely on observations than logic. That it's good to be open-minded and open to criticism. That it's good to check your beliefs with others. And that it's good not to form your conclusions before you've seen anything. When you demonstrate to people that the institution of science, at least when it operates well, embodies these values that they find important in life, they have more reason to trust it over institutions that don't update their views, that select their conclusions in advance based on political ideology, say, or that rely solely on appeal to authority. Science relies on observations and logical deductions. It's open to criticism, and scientific research is usually picked apart by fellow scientists before it can be published or shortly afterwards. Science updates its views based on new observations and is open-minded to new ideas. Good scientists are willing to be honest with you about how they came by their beliefs, the limits of those beliefs, and they're willing to change their beliefs if they can be consistently demonstrated as false. Good scientists will tell you about their uncertainties and why they remain uncertain, and even where they can act to reduce that uncertainty. Often so much so that their tentative answers can seem buried in caveats compared to the false certainty of people who have other motivations in mind than the truth. The greatest rewards in the scientific community aren't for reinforcing existing paradigms. This idea that scientists are all in it together to advance this consensus is not true. Instead, the greatest rewards come from coming up with totally new discoveries or theories that can persuade people to abandon the old paradigms. For this reason, people in a given scientific community, climate scientists certainly, lately epidemiologists too, can often feel a little exasperated when someone suddenly chips in with their new theory. I mean, I always feel like, don't you think someone would have thought of that already? Don't you know how many people are trying to think of these things and overturn existing paradigms and make a name for themselves by working on something new? And if it was demonstrably correct, don't you think they would have won the Nobel Prize? Yet perhaps this arises from the fact that scientists are so often presented in this monolithic way, particularly when we are trying to persuade people that something is accurate, and therefore many don't realise that their criticisms or objections were fiercely debated in the literature 10 or 20 years ago. It's not a case of dogma, where all of these things are being immediately rejected by an establishment, but instead the body scientific has expelled them over time, just as other ideas were taken into the fold because they had more evidence to back them up. If anything, part of the issue surrounds popular perceptions of science. Science isn't some vast monolith where everyone agrees with each other. Consensus is often hard to come by, and when it exists it's usually the product of bitter disputes between rival sources of evidence over many years and decades. Equally though, we too often romanticise the image of the single, lone genius who discovers something that totally overturns everything that was previously believed to be correct. This is a wonderful narrative, of course, and it's far more exciting to discuss the relatively rare stories of such individuals as our perception of how science works and how it advances. We fall into the same problems on this show sometimes because when we're trying to explain ideas in science, falling back on this hook of the individual narrative is so tempting so often. But increasingly in the modern era, the real story is collaboration, incrementalism, painstakingly working out which new ideas and theories have evidential support and which ones can be discarded. If we focus too much on the myth of the lone genius, we can lose the gains and the credibility of the hard-fought consensus, because 99 times out of 100, when some lone maverick comes up with a theory that flies in the face of all conventional understanding on a topic, they end up being wrong, and history forgets them. But these are the stories we don't tell. At its worst, this focus on the lone genius can lead to pathological individualism, the belief that new knowledge can only be manufactured by lone mavericks who overturn the stolid consensus, and the presentation of science as advancing by breakthroughs rather than incremental exploration of alternative options, all of which is incorrect and damaging. Scientific knowledge should be corroborated, and the mechanisms for finding it should be reproducible. Scientists can disagree with each other, and they can be wrong, but they show they're working and the evidence that they rely on. So, Professor Collins argues, your trust in scientific conclusions should rest not only on the track record of science, but also on the openness, collaboration, and expertise of those making the claims. Of course, science and the scientific method can point to an astonishing track record of successful predictions, or to mountains of evidence, thought, and theory behind what they say. They can point to the great achievements of science compared to other systems for forming belief and making predictions as evidence that it is one of the best ways to accumulate, generate, and refine knowledge of how things work. But they can also point, where that doesn't work, to the set of values that means you should trust their conclusions. And it's important for those of us who are in favour of science as the best mechanism we have for understanding and improving our world to remember precisely what these values are and aspire to stick to them as closely as we can, both in our own work and in our communications with others. But this can require sometimes a change in perspective and maybe even a change in messaging from the sciences and those that promote them. Most of all, we must stay true to the mission of the sciences, not as servants of profit or privilege, but of seeking truth so that we might all live better lives. Thank you for listening to this episode of Physical Attraction. You can find us on the web at physicspodcast.com or on Twitter at physicspod. On the web you'll find ways to donate to the show via PayPal or the Patreon. Your support is greatly appreciated. You can also contact us there. Go straight to my email. I try and answer as many emails as I can get. One thing you can always do for the show is to tell as many interested people who may want to listen to the show about it. Stick it on your social media, do all sorts of things like that, and generally spread awareness of the show. We're an independent podcast, it's just me doing this, so I rely on you guys for as much help as I can get. Until next time then, take care.